Now we move to the reaction ratio. We can translate reaction ratio as the static enthalpy rise in rotor to that static enthalpy rise in the stage. So that means, not to get confused, that H2 minus H1 occurs at the rotor, and H3 or enthalpy 3 minus enthalpy 0.1, this is the static enthalpy that occurs across the stage. That means that it passed the rotor and the stator as well. And mathematically we can write it down as R, or reaction ratio, equal to the ratio between a static enthalpy H2 minus to the static enthalpy H1. So this is belongs to the rotor outlet, this is at the rotor inlet, and this is the static enthalpy rise across the stage H3. This is occurs at the stator outlet, and this is at the rotor inlet H1, static enthalpy. And now let's see it through the relative total enthalpy, and this is the enthalpy according to the relative velocity, or W. We know that the relative enthalpy, or this total enthalpy due to the relative velocity, is equal between the inlet and the outlet of any rotors of axial compressors. So we can rewrite the static enthalpy rise across the rotor, or H2 minus H1, as a function of the relative velocity. So this becomes H2 minus H1 is equal W1 to the power of 2 minus W2 to the power of 2 divided by 2. As we are working with the axial flow machines, we know that the absolute velocity at the inlet of the rotor is equal to the absolute velocity at the outlet of the stator. So C1 is equal to C3. So we can write down that this static enthalpy rise between the rotor, the stator, and so on, or across the stage, across a single stage, H3 minus H1, can be written as a function of the total enthalpy rise across the stage, that is equal to U, or the rotational speeds of the blade or the impeller, minus to the tangential component of the absolute velocity at the outlet of the rotor, minus to the tangential component of the absolute velocity at the inlet of the rotor. So then we can rewrite the reaction ratio from this and rearrange it with this, and it becomes as a function of the relative velocity and the tangential component of the absolute velocity. If we look back at the velocity triangle, the relative velocity at point 1, or the inlet of the rotor, we can write down as a function of the axial velocity plus the tangential component of the relative velocity. So W1 is a function of CA plus WX1. This is at the inlet. And W2, we can write it down as CA to the power of 2 plus WX2 to the power of 2. This is the conditions at the outlet of the rotor. And this part of the equations remains the same for this. And as we know that CA to the power of 2 will cancel to each other as they are minus. And then we can write down the equations for WX1 to the power of 2 minus WX2 to the power of 2, and rewrite it as WX1 plus WX2 multiple with WX1 minus WX2. And another look to the velocity triangle, we can see that the tangential component of the absolute velocity at the outlet of the rotor is equal to the rotational speeds of the blade, or U, minus to the tangential component of the relative velocity, or Wx2, and it is also the same to the conditions at the inlet. So we can combine these two equations and write it down as Cx2 minus Cx1. It will cancel u on both sides, then we get Wx1 minus Wx2 equal to Cx2 minus Cx1. And we can put it back to these equations, as we know that the reaction ratio is a function of this and this, and it becomes, after combining it with the absolute velocity or the tangential component of the absolute velocity that is also part of the equations, and we can simplify it as reaction ratio becomes the tangential component of the relative velocity between the inlet plus to the component at the outlet divided by 2 times the blade speed of the rotor. Or we can also look from the perspective of the axial velocity and the relative flow angle, or beta. This is at the inlet and this is at the outlet of the rotor, and it becomes, the reaction ratio becomes Ca multiplied with tangent of beta 1 plus the tangent of beta 2 and divided by 2 times the blade speed. Or we can combine this as a function of tangent beta 1 plus tangent beta 2 divided by 2, that is equal to the tangent beta infinite. So this is another simplifications of the equations, that reaction ratio can also be a function of axial velocity divided by the blade velocity multiplied with the tangent of beta infinite, that is the functions of the relative flow angle at the inlet and the outlet of the rotor. According to the equations on the previous slides, we can draw 3 types of velocity triangle of an axial compressors. That is, when the reaction ratio equals to 0.5, and then there is a chance that the reaction ratio is higher than 0.5, or when the reaction ratio below 0.5. Now let's say that this is velocity triangle A, B, and C. For case A is when the reaction ratio is 0.5. This is where exactly the left side and the right side of the velocity triangle is identical. That means that the inlet and the outlet of the rotor are the same, that the static enthalpy and the temperature rise in the rotor and stator are equal. That's for point A. We can clearly see that they are share the same shape, just being reflected one to another. And for case B is when the reaction ratio is higher than 0.5, and we can see that the velocity triangle is skewed to the right, as beta 2 is bigger than alpha 1, and at this case the static enthalpy rise is bigger or greater in the rotor than the stator. And for the case C, or the third velocity diagram, where we see that the reaction ratio is lower than 0.5, this is the case where the static enthalpy and pressure rises are greater in the stator compared to the one in the rotor. And we can see that in this case the velocity triangle is skewed to the left side of the graph. And as we can see here at the inlet, that the relative flow blade angle is bigger at the inlet and then it's getting smaller at the outlet.